The first filter we are going to describe, that is a low pass filter. The circuit diagram is shown in the chart, and it is a passive filter that is comprises of resistor and capacitor inductor. So how the cutoff frequency is observed and how it is measured mathematically, that we will do in this lecture. So for this circuit, when we will go for the transfer function, then it is basically the Laplace transformation of output over Laplace transformation of input. So this will be given as E naught S upon EIS. So it is given as 1 upon 1 plus RCS. So this is the transfer function. So how we are getting this transfer function? Then we can apply KVL in the circuit. So it is EIT, that is our input voltage, current plus voltage across the capacitor. And what is the voltage across capacitor? That is equivalent to the output voltage, because both are in parallel, and it is given as 1 upon C integration IT dt. So when we will take the Laplace transformation of the first and second equation, then we will get the first equation will be like this. And this voltage across this capacitor, that is equivalent to the output voltage, and that will 1 upon So we'll replace this VC here, then we will get now replacing the VC, it will give us so now we are having equations in the Laplace domain. Now let me see here. From this relation we can determine the value of current in Laplace domain, that is E naught S into CS. Now replace this value of current in this third equation. So finally we will have IS, we will take common, and the value of IS is this quantity E naught S CS R plus 1 by CS. So finally when we will solve this equation, then we will have this transfer function, that is a ratio of these two. One very important parameter, that is the sinusoidal transfer function. When we talk about the sinusoidal transfer function, then from a transfer function the sinusoidal transfer function is obtained when we replace the Laplace operator by j omega. So by applying this we will get the transfer function in this form. Let the transfer function is, this ratio is given by a letter, that is G, that is indicating the transfer function. Then it will be 1 upon 1 plus RC j omega. So this is the sinusoidal transfer function. When you talk about the gain, magnitude, what is the magnitude of the gain? So this is a transfer function. Now we want to determine the gain, then it is the magnitude ratio of the output over input. So the gain of the filter, that will be given by 1 upon the magnitude of this equation, the magnitude of this j omega, that will be 1 plus RC omega square. Let RC is given by a factor or a constant, that is tau, that is a time constant. Then this gain, that is basically mod of j omega, it is 1 upon 1 plus so this is the gain. When we talk about this gain, and when we do the frequency domain analysis, when we go for the frequency response analysis, then this gain drops to 0.707 at cutoff frequency. So at the cutoff frequency, when omega equal to omega c, at the cutoff frequency, this gain will drop to 0.707. So it may be written as, because the gain is reducing to 0.707 at the cutoff frequency, so it may be written as 1 plus, so this is the cutoff frequency. So finally, when we will solve this, so at the cutoff frequency, because the gain is dropping to 0.707, so the cutoff, when we will solve this equation, we will get omega c equal to, and as we know, omega c is 1 upon RC, that is actually will 1 upon tau. So it will give us this relationship. Already we are having this relationship at this point. So the cutoff frequency is now 1 upon RC, and when we talk about the cutoff frequency, then the cutoff frequency and the omega c, it is omega c may be written as 1. So this is the cutoff frequency in hertz. This is in hertz, so it will be 1 upon RC. So finally the cutoff frequency is written mathematically as 1 over 2 pi RC. So this is the cutoff frequency of a low pass filter in hertz, and omega c is the frequency response. Omega c is the cutoff frequency in the frequency response analysis curve or diagram. So when we will go for the as we will vary the omega, that is in radian per second. So and on the y scale, when gain is plotted, that is the magnitude of E naught upon EI. So if it is the required gain, that is 1.0, and this is the gain at the cutoff frequency, so the output of a low pass filter, the frequency response of the low pass filter will be like this. So here the gain is dropping below 0.707, so this frequency is the cutoff frequency, and its value, it is related with the cutoff frequency as 1 over 2 pi. So on the basis of the resistor and capacitor value, we can determine the cutoff frequency of a low pass filter. What is the value of the resistor and what is the value of the capacitor? That will indicate the cutoff frequency. So this is the practical relationship between the cutoff frequency and the gain, the frequency response analysis curve. When you talk about the ideal behavior, ideal curve or ideal response of a low pass filter, then generally it is in the form of like this. If it is gain, and this is the, so at this cutoff frequency, if this is the desired response, then the response will be like this. At the cutoff frequency, suddenly it will come to 0. As the frequency is increased above the cutoff frequency, the gain will drop to 0 instantly. So this is the ideal behavior, but we don't get the ideal curve. So this is the practical curve that we observe in most of the cases. So this is all about the low pass filter, how the cutoff frequency is observed. In the next section we will go for the high pass filter and its analysis. Thank you.